This is IAT355 Visual Analytics, Lecture 5, Visual Perception. Like previous lectures, we're going to cut this lecture into 4 segments. The first segment is going to be about a simple model of visual perception, and we're going to immediately move to Preattentive Processing, which we'll explain in a bit. The next lecture segment will be about perceptual properties, lightness, color, and other things that you can see. The third lecture segment is going to be about nonlinear perception, that is to say, ways in which the thing that you draw on the screen does not get perceived in exactly the same way you intended it geometrically. And finally, we will talk in lecture segment 5.4 about integral versus separable visual dimensions and how they can affect the perception of data plotting. So first, let's talk about perceptual processing. And one of the reasons why we're talking about this stuff is that we seek to better understand visual perception and visual information processing for the following reasons. One of the reasons is we'd like to have some insight from perceptual science as to why do some techniques used visually work well and why others do not. We also need to know what limits do people have in terms of visual perception. We all have limits in our capabilities of how to perceive things visually, and it's good to know what those are so that we don't make mistakes about going beyond the limits when we're attempting to communicate visually. Finally, it can be useful when you're presenting or designing a visual information that you have, in addition to your professional expertise, perceptual explanations that can help explain and support the design decisions that you've made. Okay, so the simple model that we want to talk about in this lecture segment is a very simple model. It's a 2-stage process of visual perception. And the way it works is the eye is located here on the left, and it is feeding information to 2 stages of our perceptual neurons in the brain. The first stage is early parallel detection of color, texture, shape, and spatial attributes. And these things occur immediately after photons have hit the eye, been picked up by your rods and cones in your retina, and the information from those cells is passed on to neurons at the earliest stages of visual perception. In stage 1, it's a highly parallel process that extracts low-level properties of a scene, low-level in the sense that the properties are very, very local, very near to each other geometrically out in the scene, or at least the image of those things in the eye. There's a significant communication among neighboring neurons in the early stage of the visual cortex in stage 1. Stage 2 is where serial processing of object identification that may have been picked up in stage 1 using memory and spatial layout and action takes place. In stage 2 is where we do sequential goal-directed processing. In stage 1, there is very, very limited conscious action or control of what's going on in that stage, other than pointing your eyes at something in order to acquire visually a target. In stage 2, that's where conscious attention and conscious perception acts to attend to what's being seen, to attend but what's being picked up by the eyes, and to interact mentally with what's going on out there in the visual world. And because attention is being paid to things in stage 2, it's slower and is goal-directed. So let's talk a little bit more about stage 1, the low-level parallel element of what our eye is doing. So neurons in the eye and brain are responsible for different kinds of information, and they all work together to put together a percept, so to speak, the way we see the world. We have elements that detect orientation, elements that detect color, texture, movement, and arrays of neurons in our brain work together in parallel to very rapidly and automatically perceive the world. That's the strength. It's very fast and it's parallel. The drawback from the point of view of using the visual perception system as if it were a machine is that the information that is processed in parallel and processed rapidly is transitory. And it's briefly held in this thing called the iconic store. And that iconic store is constantly being overwritten, probably 5 to 10 times a second as you look out in the world. And every time you look out in the world and you look at something, if that scene changes, the preceding image, as it were, that was in your mind's eye is overwritten by the current scene. And this iconic store is the kind of thing that gives rise to things like change blindness and other kinds of blindnesses, because that image is present very briefly in the processing system, in the low-level parallel processing system. And what goes on there is a so-called bottom-up data-driven model of processing. That is to say, the information comes in, and that visual information is integrated across the scene that is perceived by your retinas. And the way in which we tend to refer to that is something that is called preattentive. Why is it called preattentive? Because this processing is done without the benefit of any attention whatsoever. We can direct what our eye is looking at, but the content of what the eye is perceiving in this low-level parallel way isn't directable by our conscious mind. At stage 2, which takes its information from the outcome of stage 1, it splits into subsystems for object recognition and for interacting with the environment. There's increasing evidence in the perception literature that supports the independence of a system for symbolic object manipulation and another system for locomotion and action. The first system, the symbolic object manipulation one, then interfaces to the verbal and linguistic portion of the brain, the part of your brain I imagine you're using right now to understand the lecture, and the second portion, with locomotion and action, interfaces to the motor system that control muscle movements, and so on and so forth. It's the presence of these two systems that allows us to be able to have a conversation while driving a car, for example. Another way to create supporting evidence for these two systems is there's an interesting phenomena called blind sight among certain brain-injured individuals, in which they are not capable of seeing the world. They report that they do not have any conscious sense that there's a world out there that they can see. But if you throw, a Nerf ball at them, they are able to catch it. And what that means is that the brain injury has affected their symbolic object manipulation centers, but it has left the locomotion and action part of it intact. And so if you throw something at them, at a person with this injury, they're able to react to it, but they aren't able to tell you what color the ball is and what its texture is until they hold it. So, in any case, there are two systems. Stage 2 attributes are, as I've mentioned earlier, slow and serial. And the reason why it's slow and serial is that it involves working memory and long-term memory. And what goes on there is what you might call top-down processing. That is to say, the top is your conscious mind saying, I want to look at this, I want to interact with that, and it is driving what part of stage 2 is attending to the information coming from stage 1. And the fact that you're seeing only what you're paying attention to, largely, is what gives rise to the various forms of change blindness that occur in the system. The different forms of change blindness then overriding the image store, the iconic store in the previous slides. Okay, so now that we've talked a little bit about this very, very simple model, let's talk about how stage 1 capabilities can be used in visualization. So the question there is, how does the visual system analyze images? Some things seem to be done perfectly capably by stage 1 actions. That is to say, they can be done very rapidly within 200 to 250 milliseconds, and before you need to actually pay conscious attention to them. And I'll show you how a little experimental apparatus just a little later on that indicates that things can be done very, very rapidly, that each of us can do these things very, very rapidly. By rapidly, once again, we mean 200 or so milliseconds, or 1/5 to 1/4 of a second, and it seems to be done by this low-level parallel vision system, stage 1. So let's start with an example. So what the question is here is, how many 3s are in this big old block of digits? Now count how many 3s. Now, this second block is identical to the first one. You can see the digits are the same as I scroll back and forth. But in the second one, it's a lot easier to see the 3s because, of course, they visually contrast with all of the other digits in this field of distractors, or the non-3 digits, 0, 1, and 2, and 4 through 9. They are distinct visually from what is now background images because there's a significant luminance difference between the digit 3 and digit 8, 9, and 7 in the rest of this field. What enables us to see those things rapidly is our preattentive capabilities of detecting a target that is distinct from other possible targets in the background, not just the white area here, but the array of distracting digits. The fact that they're visually distinct enables us to preattentively detect the 3s and count them to a limited degree. So, what kind of tasks can be done preattentively? Well, the first thing is target detection. I asked you just a moment ago to detect 3s, and when all the 3s look like all the 6s and the 9s and the 8s and the 2s, it's hard to find them. That's one of the reasons why herd animals like wildebeest or bison all look like each other. It's so that predators can't focus on a single individual to hunt it down. So target detection is a very important fundamental thing, and our preattentive system is very good at target detection, at noticing something that is distinct from other things, particularly if we can readily identify it visually as well as by other means, like having a name for it. Another thing that is preattentively capable is boundary detection. That is to say, can you detect that there are a number of elements that can be grouped together? And this is the kind of thing that we mean when we say we're looking for clusters. We're looking for a bunch of items, say plotted data points, that are grouped together and can be distinguished from the rest by having what seems to be a visual boundary around them. And finally on this list, counting. How many elements of a certain type are present? We can count up to a low limit of roughly a handful, but we can certainly do a certain amount of counting even in a very rapid time within 200 or 250 milliseconds. Okay. So now what I'd like to be able to do is I'd like to talk about some examples of things we can detect and things we can't detect preattentively. So I'm going to show you an example of locating something that we can detect rapidly. So the question is there a red circle in 2 fields of distractors? Is it to the left or to the right? So it probably took you no more than 200 milliseconds to be able to say to yourself, yeah, buddy, there's a red circle on the left. Thank you, that was just too easy. So this kind of thing can be done very rapidly, as we also saw with the field of 3s in a few slides back. It can be done rapidly because we can name the thing we're looking for, we can name the target that we're looking for, and it's easy to visually distinguish red from blue. It's a fundamental property of the dots in this scene. Now what I'd like to do is I would like to present a number of visual tests that have been done by a prof at North Carolina State University named Chris Healey. And the reason why we mention him is because he did his degree at UBC a number of years ago, and he specialized in the study of this kind of stuff a number of years ago. Okay, so here is an element of his website that's about perceptual processing and preattentive perceptual processing. He summarizes it PP here. And what I'd like to do now is I'd like to present a number of preattentive stimuli. And what I'm going to ask you to do as we go forward is ask you if you can see the red circle. So let's start off with a small number of elements, 10 elements, and we're going to do 2 trials. And we're just going to leave the exposure time to be 200 milliseconds. I'm using this thing because it reliably delivers a 200 millisecond stimuli to you, and it does work in the YouTube video. So let's just start. what it will do is it will present the image, and it will then put it away and then tell you, perhaps redundantly, whether it was there or not. And just see if you can see the target, and then see if it matches up with the text that follows. Here we go. So in that pair of stimuli, we saw an array of blue dots kind of randomly located, and one of them had a red dot, the other did not. Let's do some more elements. Let's do 70. And you'll notice we're still capable. Here we go. So right there, it was the first one didn't have a red dot, and the second one did have a red dot. And even though there were 70 items, you could see it right away. You didn't have to think about it. You didn't have to worry about it. It was right there in your face. And that's what we mean by preattentive processing. Can we rapidly detect the presence of a target that we're looking for? And if the target, if all the targets are circles and one of them is red, we're pretty good at detecting that. So now what I'd like to do is to see if we can do the same with shape. So we have a number, once again, 70 elements, and we're going to start by putting up a red circle in a field of red squares. Here we go. So that one's just a little harder. I'm going to run another round of 2 trials. Here we go. So once again, you can detect visually whether or not there's a red circle that's present in that field of red squares. So once again, color and shape are both things that we can detect preattentively. It's pretty easy when all but one of the targets is not what you're looking for, and maybe one is with the thing you are looking for or not. Now what I'm going to do is I'm going to make this task a bit harder. I'm going to ask if you can, in a field of distractors that are either circles or squares or red or blue, if you can see a red circle. And what I'm going to do now also is I'm going to cut the number of items down to 15. Here we go. And the option here is conjoin. That is to say, we're going to mix shape and color together. We know that color works and that shape works, even with a lot of distractors. Now let's try to put it together. So here we go. Now, you might have been lucky and put your eye on the target in the one where it was present. Let's do a couple more. So for me, I wasn't able to see the one where it was present. And the reason why that's hard is because color and shape is difficult to conjoin except if you involve your conscious mind. So if your eye happens to be pointing at the location where a red circle, the thing you're looking for, actually is, you're good. You see it. But if your eye isn't pointed at that location, then you likely don't see it. It's there, but you're not able to detect it preattentively. And the reason why you're not able to detect it preattentively is the image isn't up there long enough for you to be able to bring your conscious mind to bear. The other thing that's very important is I'm using this application to show the target, the stimulus, for only 200 milliseconds. I'm not giving you the opportunity to sit and stare at it. And indeed, the fact that there's a blank that follows the presentation of the stimulus means that you're not able to continue to re-access it in your iconic store. The iconic store is overridden by white and overwritten again by the word present or absent or whatever the words are that Dr. Healey's using here. Okay, so that's it for that. So what I'd like to do is do one last test, and I'd like you to tell me, is there a red square? Yes, there is. It's in Moscow. Alrighty. So, what we've shown there is how you can preattentively detect whether or not targets of a particular kind are present or absent. And we've demonstrated that you can see them very rapidly without the necessity of conscious work. But when you start to mix things together, shape and color, then you need your conscious mind to be able to reliably see the thing in a short time. And if your eye's on the target, you win. If your eye's not on the target, you're not able to detect it. What's going on there is that your conscious mind needs to be brought to bear. And that means it's no longer pre-attentive, but attentive, because conscious mind means that you're attending or have your attention paid to the stimulus. Okay, so color and shape are not the only things that are pre-attentive. Here is a couple of examples of the locating a boundary, either a horizontal boundary or a vertical boundary. And in this case, on the left, we clearly see a horizontal boundary. What's going on is that we have white circles and squares in the upper 2 rows and black squares and circles in the lower 3 rows. And we can do that pre-attentively. You can see it right away. On the right, it's a lot more difficult because we have white squares and black circles, right? White squares here and here, and black circles in the rest. And to the right of this vertical boundary, there's black squares and white circles. But because we're mixing shape and color to be representatives of the stuff on the left and the stuff on the right, you have to involve your conscious mind. And it's so much work that you cannot see the vertical boundary that exists right here. Okay? And so that's an example where sometimes you can do it pre-attentively if there's a single feature. But if you have a pair of features, or perhaps more, but in this case it's just a pair of features, you can no longer do it pre-attentively. Okay. So, for pre-attentive features, certain visual forms lend themselves to pre-attentive processing. And a variety of visual forms seem to work. So let's talk about some other variations of things that seem to work and things that are harder. So 3D seems to work as a pre-attentive property. On the left, we can rapidly see that there is a group of 4 items, 2 by 2, of these cubes. The distracted cubes are all, in some sense, the right side up, with the lightest part at the top, and the darkest face is being in shadow, and maybe it's getting a little bit of light on the left. And this one is either rotated 180 degrees and therefore is upside down, or we're looking on the inner face of the cube. It doesn't matter which interpretation. But because we're used to seeing 3D objects, we kind of get very rapidly that those things are different. On the right, even though the components are the same, we have a little bit of a harder time detecting that there is also a 2 by 2 array of the distracting items here in the middle. The elements are the same. There's a white diamond, there's a gray rhombus and a black rhombus, although they're smaller in these ones than they are over here. But because these things are not composed as a 3D shape, it's harder to detect the fact that these are rotated versions of these other ones. It doesn't really leap out at us the way the 3D shapes do. Another thing that can also be rapidly detected is basic features such as enclosure. So here we have, again, composed out of the same 3 visual elements, a vertical line segment, a horizontal line segment, and a diagonal one. We see a 3 by 3 array where the same components are used, but they're arranged differently. These ones are enclosed, the triangle's enclosed, and these ones are not, they're open. It's easier to see this array than it is this one. It just takes a little bit more time. You can see it eventually, but these triangles are rotated, so we don't have the cue of enclosed or not in this one, this array of triangles in the lower right. So the potential pre-attentive features are things like length, width, size, curvature, number, terminators, and so on, as you see on this list. And perceptual psychologists over the years have tested each of these things to find how well they work as pre-attentive features. And what I'm going to do now is show an example of 8 of them. So here is a set of distractors with one or maybe a few different items, and you can see them very rapidly that there are different ones. So here we're using orientation to distinguish the item. This one we're using length and width. Here we're using closure or not closure. All of these are not closed except for the circle. We're using size in this one very quickly. We're using curvature here and density here. There's a tighter grouping here than the others, and our boundary detection is kind of being triggered there. And we're seeing a number and also angle and color, which we've seen quite a bit already. Next, I'd like to show Healey's webpage again. And in this one, I'm showing his page because these are animated GIFs, and so you can see the motion that's present in these three on the lower left. So this one's a little bit harder to see because it's about binocular vision, and I can't show that in a monocular display on a single screen. But we can rapidly see intersections. It's a fundamental feature that we can see very rapidly. Also terminators, line segments terminating versus, similar line segments, but there's not a sense of letter T versus L here. We can see 3D depth cues reasonably well, and we can also certainly see flicker. That's something that every advertisement on the web uses. As well as direction of motion, we can rapidly see that this thing's moving in a different direction to everything else. And also velocity of motion. We can see that this thing's kind of moving faster or something. And all of those features are very easy for us to detect visually and rapidly without the necessity of conscious thought. And part of the reason these motion ones, you see those used in advertising a lot, is they're trying to attract your attention by distinguishing themselves from what is hoped to be static content in, say, the rest of the web page. Alrighty, so let's go back to the slides. And that's pretty much the end of the lecture on preattentive processing. And it's based on a simple model of visual perception in which the first stage, getting information directly from the eye, operates rapidly and in a parallel manner, and the second stage uses conscious attention to be able to drive what we're looking at.